Everything you experience as solid is a negotiated illusion. At the scale where physics actually decides outcomes, atoms never touch, surfaces never meet, and matter never presses back in the way intuition demands. What holds the chair beneath you, what keeps planets from merging into featureless density, is not contact at all, but a quantum rule, enforced by electrons, silent, unseen, and absolute. For anyone who studies fields, interactions, and cosmic structure, the electron is not a minor character in the Standard Model. It is the mediator between light and matter, the gatekeeper of opacity, reflection, and stability. Without electrons, photons would pass unhindered, atoms would fail to assemble, chemistry would vanish, and the universe would remain a smooth, unreadable plasma. Texture itself, both physical and informational, begins here. Tonight we enter that layer of reality where solidity dissolves into exclusion, and certainty gives way to structure born from constraint. We start by dismantling the idea of contact itself. Why does every solid thing you touch depend on something you can never see, the electron? Everything that feels solid begins with a refusal, not a force pushing back, not atoms colliding like tiny billiard balls, but a rule written deep into quantum mechanics. Certain things are simply not allowed to be in the same state at the same time. When you sit on a chair, when your feet rest on the floor, when your body maintains its shape against gravity, nothing is truly touching anything else. Between the nuclei of atoms there is vast emptiness by any physical measure. What you experience as resistance is the consequence of electrons enforcing a prohibition, one that cannot be overridden, negotiated, or weakened. This is the quiet shock at the heart of matter. Solidity is not a property of material substance in the classical sense. It is an emergent outcome of the Pauli exclusion principle, the rule that no two electrons with the same quantum identity can occupy the same quantum state. When the electron clouds of atoms are pressed toward one another, they do not compress indefinitely. They reorganize, resist, and ultimately refuse overlap. That refusal is what your nerves interpret as hardness. Without electrons, there would be nothing to resist collapse. Atomic nuclei, stripped of their electronic structure, would fall together under electromagnetic attraction and gravity, forming dense, featureless matter with no surfaces, no chemistry, no boundaries. The universe would still exist, but it would be unreadable. No textures, no materials, no stable complexity. The richness of the physical world begins not with mass, but with exclusion. To understand why this matters, it helps to abandon the image of electrons as tiny orbiting beads. That picture, useful in its time, hides the real mechanism at work. Electrons are not little objects tracing paths around nuclei. They are quantum state solutions to equations that describe how probability is distributed in space. When many electrons are present, as they are in any solid object, those states must arrange themselves so that no two identical electrons violate Pauli's rule. The result is structure, shells, bands, and energy levels that cannot be compressed beyond certain limits. This is where solidity quietly emerges. When you press your hand against a wall, the electrons in your skin and the electrons in the wall are forced into closer proximity. But instead of merging, they reorganize into higher energy configurations. Energy rises sharply, and that increase manifests macroscopically as resistance. Your hand stops, not because matter has collided, but because quantum states have reached an enforced boundary. The astonishing part is how universal this mechanism is. The same principle that keeps your body from falling through the floor also governs why metals conduct electricity, why insulators do not, and why materials differ so dramatically in hardness and elasticity. Diamond resists deformation, not because its atoms are stronger in any classical sense, but because its electrons are locked into rigid, deeply constrained bonding states. Rubber yields because its electrons can rearrange more easily. The difference is not substance, it is quantum permission. This perspective reshapes how we understand matter itself. Classical physics imagined solidity as a result of repulsive forces acting at short distances. Quantum mechanics replaces that picture with something subtler: constraint without contact. The electron does not push back like a spring. It simply cannot be placed where another identical electron already exists. The universe, at its most fundamental level, is governed as much by rules of exclusion as by forces of attraction. That rule also explains why light behaves the way it does when it encounters matter. When a photon strikes a surface, it is not bouncing off a hard boundary in the everyday sense. It is interacting with electrons. The photon's electric field couples to electronic states, temporarily exciting them. Those electrons then re-emit the energy, sending the light back into space. Reflection is not a surface phenomenon. It is an electron phenomenon. If electrons did not exist, or if they did not obey Pauli exclusion, light would pass through matter almost unhindered. There would be no mirrors, no opacity, no shadows. The universe would be flooded with radiation that never found anything to interact with. Stars might still burn, but their light would travel endlessly without leaving an imprint. Observation itself would be impossible. This is why Richard Feynman could say without exaggeration that all of chemistry is nothing but the dance of electrons. Chemical bonds are not little hooks connecting atoms. They are shared or exchanged electron states arranged under the strict accounting rules of quantum mechanics. Molecules exist because electrons find configurations that minimize energy while respecting exclusion. Change the rules for electrons, and the entire periodic table dissolves. The same logic scales upward into condensed matter and astrophysics. The rigidity of a crystal lattice, the pressure inside a white dwarf star, and the stability of matter under extreme compression all trace back to electron degeneracy. In white dwarfs, electrons are packed so tightly that exclusion pressure becomes a dominant force, resisting gravitational collapse even when nuclear fusion has long ceased. The star does not explode or implode immediately because electrons once again refuse to overlap. Here, solidity becomes a cosmic principle. What keeps a dead star from collapsing further is the same quantum rule that keeps you from sinking through your chair. Different scales, same mechanism. This continuity is not poetic coincidence. It is the hallmark of fundamental physics. Even temperature, which we often think of as a measure of motion, is deeply tied to electron behavior. In solids, heat propagates as vibrations of atomic lattices, phonons, but the capacity of a material to conduct or store thermal energy depends on how electrons are allowed to occupy energy states. Metals conduct heat well, because electrons can move between closely spaced states. Insulators trap heat because their electronic states are separated by large energy gaps. Once again, exclusion shapes experience. What makes this especially striking is how indirect our access to electrons really is. We never see them as objects. We infer their presence through scattering patterns, spectral lines, and macroscopic effects. When experiments probe matter at finer scales, they do not reveal tiny solid grains of electron substance. They reveal probability distributions, interference patterns, and constraints. The electron announces itself not by presence but by limitation. This is why the solidity of matter feels so counterintuitive when examined closely. Our senses evolved to navigate a world where these quantum rules operate flawlessly in the background. We feel firmness and assume substance. Physics reveals instead that firmness is an emergent signal, a macroscopic translation of forbidden configurations at microscopic scales. The Pauli exclusion principle is often introduced as a technical rule for fermions particles with half-integer spin, but its consequences are anything but technical. It is the reason atoms have size. Without it, electrons would collapse into the lowest energy state around nuclei, and all atoms would shrink to nearly the same dimensions. The diversity of chemical elements would vanish. There would be no carbon frameworks, no complex molecules, no biology. From this angle, the electron becomes less a particle and more a structural rule embodied in nature. It enforces differentiation. It creates layers, shells, and hierarchies. It allows matter to be extended rather than point, like textured rather than smooth. The universe gains architecture because electrons are not allowed to agree too closely with one another. This also clarifies why solidity is not absolute. Under sufficient pressure, materials deform, melt, or collapse into new phases. What changes is not the existence of electrons, but the available quantum states. As pressure rises, electrons are forced into higher energy configurations or reorganized into collective behaviors. Eventually, even exclusion pressure can be overwhelmed, leading to exotic states of matter found in neutron stars and beyond. Solidity has limits, and those limits are written in quantum mechanics. Seen this way, your everyday experience is perched delicately atop deep physical law. The calm reliability of surfaces depends on rules discovered only in the 20th century, rules that have no classical analog and no intuitive explanation beyond mathematics. That reliability is not guaranteed by matter itself, but by electrons behaving exactly as quantum theory predicts. And that is perhaps the most remarkable aspect of all. The universe does not feel solid because it is made of solid things. It feels solid because it obeys rules that prevent sameness from collapsing into uniformity. The electron, invisible and indivisible in every experiment so far, is the quiet enforcer of those rules. If electrons are not little objects, but quantum states constrained by exclusion, what does it really mean to call them particles at all? The firmness of the world has already dissolved into probability and prohibition. What remains is to ask what kind of entity the electron actually is, when even solidity turns out to be an illusion enforced by quantum law. Calling the electron a particle feels natural only until you look closely at what experiments actually show. The word carries the weight of centuries of intuition, something localized, something that travels along a path, something that can be pointed to. But the moment physics learned how to isolate a single electron and ask it to reveal its behavior, without averages or crowds, that familiar word began to fail quietly, without drama, but decisively. The failure appears most clearly in one of the simplest experimental arrangements ever conceived. Send electrons one at a time toward two narrow openings and record where they arrive. Nothing in classical physics prepares you for what follows. Each electron is detected as a single localized event, a spot, a click, and yet, over time, the accumulation of these individual impacts forms an interference pattern, alternating regions of high and low probability that only make sense if each electron behaved like a wave spreading through space and interfering with itself. Not with other electrons. With itself, the experiment works even when electrons are sent so slowly that only one is ever in flight at a time. There is no neighboring particle to collide with, no medium to ripple through. The pattern still emerges. The conclusion is unavoidable. What spreads between emission and detection is not a tiny object following a hidden path, but a probability amplitude, a mathematical description of where the electron might be found if you choose to look. The discomfort this causes comes from language, not from the data. The electron is called a particle because when we detect it, it behaves like one. It deposits energy at a single point. It triggers a localized response in a detector. But between those moments of interaction, the theory that predicts every outcome correctly does not describe a point-like thing moving through space. It describes a wave function, a distribution of possibilities, evolving smoothly, according to precise equations. This distinction matters. The electron does not smear itself out like mist filling a room. Matter is not dissolving into fog. What spreads is information. What evolves is our predictive description. When we say the electron behaves like a cloud, we are not describing a physical substance diffusing through space. We are describing the structure of uncertainty imposed by quantum mechanics. Historically, this realization did not arrive all at once. Early experiments with cathode ray tubes in the late 19th century revealed streams of something carrying charge and mass. These entities bent in electric and magnetic fields exactly as particles should. The electron was born as a particle, because in those experiments that language worked perfectly. But physics has a habit of keeping what works until it no longer does. The turning point came when experiments began to probe electrons at scales where their wavelength could not be ignored. When electrons were diffracted by crystals producing patterns identical to those made by light waves, it became impossible to maintain a purely particulate picture. The same object that curved smoothly under electromagnetic forces also interfered, diffracted, and exhibited phase relationships. The electron was not switching identities. It was obeying a single set of rules that classical categories could not contain. What makes this especially unsettling is that nothing in the experiments forces the electron to choose a definite behavior ahead of time. The same setup can reveal particle-like or wave-like features depending on what is measured. If you ask where the electron lands, you get a point. If you ask how probabilities distribute, you get interference. The electron does not change. The question does. This is where the phrase wave-particle duality becomes misleading. It suggests a compromise between two classical ideas, as if the electron were sometimes one and sometimes the other. In reality, it is neither. The electron follows quantum rules that reduce to particle-like behavior when interactions localize it, and wave-like behavior when predictions evolve freely. The duality is in our descriptions, not in the electron itself. The key insight is that quantum mechanics does not describe what is happening in the space between interactions. It describes how to compute probabilities for outcomes. The wave function is not a physical wave in space like a ripple on water. It is a mathematical object that assigns amplitudes to possibilities. When those amplitudes combine, they can interfere constructively or destructively, shaping the pattern of results we later observe. This becomes especially clear when electrons interact with light one photon at a time. In carefully controlled experiments, a single electron can scatter a single photon, exchanging energy and momentum in a perfectly quantized way. Each interaction is discrete and localized. Yet, the probability of where that interaction occurs is governed by the electron's extended wave function. Local events emerge from non-local descriptions. The tension between these two aspects is not a failure of measurement or technology. It is a feature of reality as currently understood. No experiment has ever revealed a hidden trajectory behind the interference pattern. Attempts to assign definite paths inevitably destroy the pattern itself. The more precisely you try to say where the electron went, the less interference remains. This is not because the electron resists being known, but because the act of measurement changes the structure of probabilities. This realization forced physics to reconsider what it means for something to exist. In classical mechanics, existence is tied to position and motion. Objects are assumed to have properties whether or not anyone measures them. Quantum mechanics loosens that assumption. The electron has properties that are well defined only in the context of interaction. Between interactions, it is described by a set of potentialities governed by strict mathematical rules. This does not mean reality is subjective or dependent on observers in any mystical sense. Detectors, atoms, and fields are sufficient to produce measurement outcomes. But it does mean that the classical idea of a continuously existing particle with a definite trajectory is not supported by evidence. The electron exists as something more abstract, yet more precise, a quantum state, evolving deterministically in time, punctuated by probabilistic interactions. The precision here is often overlooked. The equations governing the electron's wave function are exact. They allow predictions with extraordinary accuracy, tested to many decimal places. What is probabilistic is not the law, but the outcome of individual events. Quantum mechanics does not tell you which spot will light up next, but it tells you, with remarkable certainty, how often each spot will light up over many trials. From a cosmological perspective, this matters deeply. The same probabilistic structure that governs electrons in the laboratory governs electrons in stars, in interstellar plasma, and in the early universe. The opacity of the primordial plasma, the formation of atomic hydrogen, and the release of the cosmic background radiation all depend on electrons behaving as quantum probability distributions interacting with light. The universe became transparent, not because particles suddenly decided to move differently, but because quantum states reorganized as conditions changed. This reframes how we think about scale. The electron does not become more classical simply because it is part of a larger system. Classical behavior emerges when many quantum states interact in ways that suppress interference and amplify localization. Solidity, trajectories, and definite paths are emergent phenomena, not fundamental ones. They arise when probabilities become overwhelmingly concentrated. Seen this way, calling the electron a particle is not wrong, but it is incomplete. It captures how electrons announce themselves when they interact, but not how they propagate, interfere, or encode information. The electron is a point of interaction carried by a wave of possibility. Remove either aspect, and the description fails. The discomfort this causes is not accidental. It signals that our everyday categories evolved for survival, not for accuracy at the smallest scales. Physics progresses by allowing those categories to break when experiments demand it. The electron is one of the clearest examples of this process, a concept stretched beyond its classical limits, yet held together by mathematics that never once fails an experimental test. If the electron is not a tiny object moving through space, but a quantum state that produces localized events, then what does it mean to ask about its size, its shape, or its internal structure? The interference pattern has already dissolved. The classical picture of motion. The next step is to ask whether there is anything inside the electron at all, or whether point-like behavior is the deepest description nature allows. After the electron dissolved from a solid object into a probability cloud, one question remained unavoidable. Does anything exist inside it at all? If the electron is not a tiny sphere and not a smeared substance, perhaps it still has an internal structure layers, components, something waiting to be uncovered at smaller scales. Physics did not leave this question to philosophy. It turned to experiment, and it did so with extraordinary persistence. For nearly a century, laboratories have tried to probe the electron's interior in the only reliable way nature allows, by striking it with light and other particles of ever-increasing energy, and watching how it scatters. The logic is simple and ruthless. If an object has size or substructure, high-energy probes will reveal it. Extended objects scatter differently from point-like ones. Composite systems betray internal length scales. Silence in this context is not ignorance. Silence is evidence. The earliest scattering experiments already hinted at something unusual. When electrons were deflected by atomic nuclei, their behavior matched calculations that assumed the electron had no spatial extent. As accelerator technology advanced, this assumption was tested again and again. At facilities like SLAC and later CERN, electrons were accelerated to energies so high that if they possessed any internal structure larger than a tiny fraction of a proton's size, it would have revealed itself unmistakably. It never did. To understand why this matters, it helps to recall how size is detected in the first place. You never measure size directly. you infer it from interactions. When light scatters from an object, the pattern of angles and intensities encodes information about the object's spatial extent. This is true at every scale. X-ray diffraction reveals atomic spacing in crystals. Electron scattering maps nuclear charge distributions. If the electron had a radius, however small, scattering experiments would show deviations from the predictions for a point-like particle. They do not. As energies increased into the giga-electron volt and later tera-electron volt range, experiments continued to find that electrons behave as if all their charge, mass, and interaction strength are concentrated at a single point, not approximately, not within error bars that could hide complexity, exactly to the limits of experimental resolution. Today, those limits extend to distances smaller than anything light can directly image, far below a trillionth of a meter. This absence is not a failure of imagination or technology. It is a quantitative result. Quantum electrodynamics, the theory describing how electrons interact with light, predicts scattering outcomes with astonishing precision under the assumption that the electron is point-like. Those predictions have been tested to more than 10 decimal places. Any finite size would introduce corrections. None are observed. At this stage, the word point must be handled carefully. It does not mean the electron is an infinitely dense dot in space, like a classical singularity. It means something subtler and more restrictive. No experiment has ever detected any spatial extension associated with the electron's interactions. The electron behaves as if it has no internal length scale. In physics, that is a powerful statement. What makes this especially striking is that many other particles did not survive similar scrutiny. Protons, once thought to be elementary, revealed internal structure when probed at high energy. Their scattering patterns exposed constituent quarks and gluons along with a finite charge radius. The electron, subjected to the same investigative pressure, remained silent. This silence reshapes how we think about fundamental entities. If the electron had constituents, those constituents would have shown themselves through deviations in scattering. If it were an extended object, its size would influence interaction probabilities. Instead, the electron responds to probes as a single, indivisible participant in every interaction. From the emotional arc we have been following, this is the moment where intuition finally gives up its last refuge. First, solidity dissolved into exclusion, then particles dissolved into probability. Now, even the hope of hidden internal structure disappears. The electron is not a tiny machine with parts waiting to be discovered. It is as simple as it can be, yet not simple in any classical sense. This simplicity is unsettling, because it offers no mechanical picture to lean on. In classical physics, explanation meant reducing systems to smaller moving pieces. Here, reduction stops. The electron has properties mass, charge, spin, but no internal anatomy that explains them. The properties simply are. This does not mean physics has given up. On the contrary, the point-like nature of the electron is one of the most constraining facts in all of fundamental science. Any theory that proposes new physics must respect it. Attempts to modify quantum electrodynamics, introduce hidden dimensions, or unify forces all face the same experimental wall. If your theory predicts electron structure at accessible scales, it is wrong. The role of light in this story is crucial. Light is our sharpest probe. Shorter wavelengths correspond to higher resolving power. By accelerating electrons and colliding them with photons or other particles, experiments effectively use light with wavelengths far smaller than any microscope could achieve. If the electron had size, light scattering would betray it immediately. The fact that it does not is not a gap in observation. It is an observed absence. In this sense, silence becomes data. Quantum electrodynamics treats the electron as a point-like excitation of a quantum field. This is not a philosophical preference. It is forced by experiment. Calculations involving electron interactions assume point-like behavior, and those calculations match reality with unmatched accuracy. The electron's magnetic moment, for example, has been measured and predicted to agree to more than 1 part in a trillion. Any internal structure would disrupt that agreement. The idea that something real can lack size challenges deeply held assumptions about physical existence. We are accustomed to believing that to exist is to occupy space. The electron forces a refinement of that idea. It exists through interactions, not through extension. Its reality is revealed in how it couples to fields, not in how much room it takes up. This also clarifies why earlier attempts to imagine the electron as a tiny spinning sphere always failed. Such models predict surface speeds faster than light and internal stresses that make no physical sense. These were not merely incomplete pictures. They were incorrect because they assumed the electron had classical size. Experiments have long since removed that assumption from the table. At the same time, point-like does not mean simple. The electron participates in a sea of quantum fluctuations. Virtual particles appear and vanish around it, influencing its interactions in measurable ways. These effects are not signs of internal structure, but of the surrounding quantum field. The electron remains indivisible even as its environment teems with activity. From a cosmological viewpoint, this matters more than it first appears. The early universe was governed by interactions between point-like particles at energies far beyond anything we can reach today. The fact that electrons remained point-like across all accessible scales supports the idea that they were already fully formed participants in the earliest moments of cosmic history. There was no gradual unveiling of substructure as the universe cooled. The electron entered the cosmic stage complete. This constancy underlies the stability of physical law. Atomic sizes, chemical reactions, and stellar processes depend sensitively on electron behavior. If electrons had hidden structure that became relevant at certain energies, the universe's evolution would have unfolded very differently. The uniformity we observe across time, across space, across extreme conditions, rests in part on the electron's refusal to reveal any internal complexity. There is a temptation to treat this as a temporary conclusion, something that future experiments will overturn. Physics has learned to be cautious with such expectations. The history of the electron suggests the opposite pattern. As resolution improved, complexity disappeared rather than emerged. Each new generation of experiments tightened the bounds on size, pushing the electron closer to an ideal point, not further away from it. This does not close the story. It sharpens it. If the electron truly has no size, then questions about its mass, charge, and role in the universe become more profound, not less. Where do these properties come from, if not from internal structure? Why does the electron have exactly the values it does, and not others? The absence of size removes one class of explanations entirely. The electron has been struck, scattered, probed, and interrogated with the highest energies humanity can produce. It has not yielded layers or components. It has yielded consistency. If the electron is truly point-like, yet carries mass, charge, and spin, then those properties must arise from something deeper than structure. To understand that, we must follow the electron, not inward but outward, into the fields that give it weight and the mechanisms that set its scale in the universe. Light does not care about most of the mass in the universe. It passes effortlessly through protons and neutrons, slips past entire atomic nuclei, and ignores vast amounts of matter that outweigh electrons by orders of magnitude. And yet the moment light encounters an electron, its journey can end, bend, scatter, slow, or reverse. This imbalance is not an accident of scale or a limitation of experiment. It is a deep structural feature of how electromagnetism is written into reality. From the path we have followed so far, this feels like a natural escalation. Solidity dissolved into exclusion. Particles dissolved into probability. size dissolved into point-like silence. Now, interaction itself sharpens around a single question: why does light interact almost exclusively with electrons? The answer begins with charge, but it does not end there. Photons are quanta of the electromagnetic field. They respond only to electric charge and currents. Protons and electrons both carry charge, yet light overwhelmingly couples to electrons. The reason is not subtle. It is mechanical, kinematic, and unavoidable. Electrons are light enough to respond. When a photon encounters a charged particle, it can transfer energy and momentum. How much the particle responds depends on its mass. Protons are nearly 2,000 times heavier than electrons. Neutrons, though electrically neutral overall, contain charged constituents that are tightly bound and similarly massive. When light strikes them, the recoil is negligible. The interaction is effectively invisible. To the photon, these objects are almost immovable. Electrons, by contrast, move. They accelerate easily under electromagnetic influence. Their small mass allows the oscillating electric field of light to shake them, drive them into motion, and force them to re-emit radiation. This is not a secondary effect. It is the primary channel through which light interacts with matter at all. This is why opacity, reflection, refraction, and absorption are not properties of atoms in general, but of their electrons. Remove the electrons, and matter becomes almost perfectly transparent. Leave the nuclei behind, and photons pass through, as if space were empty. This insight explains something deceptively familiar. When you look at a mirror, the light does not bounce off a solid surface in the classical sense. Instead, the incoming electromagnetic wave drives electrons in the metal into collective motion. Those electrons oscillate in response, generating new electromagnetic waves that propagate back into space. The mirror is not reflecting light because it is hard. It is reflecting light because its electrons are free to move. Change the electronic structure, and the optical behavior changes completely. Insulators trap electrons in bound states and transmit light. Metals allow electrons to flow and reflect light. Semiconductors occupy a narrow middle ground where electronic band structure decides which wavelengths are absorbed and which are transmitted. The material world announces itself optically through electrons alone. This principle becomes clearer when stripped to its simplest form. Consider light scattering from a single free electron. At low photon energies, the dominant process is elastic scattering, where the photon changes direction but not wavelength. This interaction is described by Thomson, scattering first, understood in the early 20th century by Joseph John Thomson in the context of classical electromagnetism. In Thomson, scattering the photon's electric field accelerates the electron, and the accelerating charge radiates. No internal structure is required. No absorption takes place. The electron simply responds to the passing wave. The cross-section, the effective target size for scattering, depends only on fundamental constants and the electron's mass and charge. It does not depend on the photon's wavelength, as long as the energy remains low compared to the electron's rest mass. Already something remarkable is visible. Light does not scatter from matter because matter is there. It scatters because electrons can move. Increase the photon energy, and the picture shifts. At higher energies, scattering becomes inelastic. The photon transfers part of its energy to the electron, emerging with a longer wavelength. This is Compton scattering, discovered by Arthur Compton, and it revealed something profound. Light carries momentum, and electrons respond to it as discrete quanta. Compton scattering cannot be explained without treating both light and electrons quantum mechanically. The shift in wavelength depends only on the scattering angle and the electron's mass. Once again, the nucleus plays no role. Even when bound inside atoms, electrons dominate the interaction. The nucleus is too heavy, too inert, too rigid to participate meaningfully. This asymmetry governs not only laboratory experiments, but the behavior of the entire universe. In the early cosmos, matter existed as a hot, dense plasma. Electrons were not bound to nuclei. Photons scattered endlessly from free electrons bouncing from one to the next, unable to travel freely. The universe was opaque, not because it was dense with matter in general, but because it was dense with free electrons. Only when the universe cooled enough for electrons to bind to nuclei forming neutral atoms did light escape. This moment, known as recombination, marks the birth of transparency. Photons were suddenly free to travel across cosmic distances without constant scattering. The cosmic microwave background exists because electrons stopped interfering. If you understand electrons, you understand why the universe became visible. Astrophysics reads the universe through this lens. Stellar atmospheres are diagnosed by how electrons absorb and emit light. Spectral lines arise when electrons jump between quantized energy levels, absorbing or releasing photons at precise wavelengths. Plasma physics, governing stars, nebulae, accretion disks, and jets, is fundamentally the physics of electrons moving in electromagnetic fields. Even in the most extreme environments, electrons remain the interface. In neutron stars, where nuclei are crushed into degenerate matter, electrons still contribute pressure and opacity. In interstellar space, where matter is sparse, electrons determine how radio waves propagate, how polarization rotates, and how magnetic fields imprint themselves on light. This is not because electrons are special in a sentimental sense. It is because electromagnetism couples to charge, and electrons are the lightest charged objects available. This lightness is everything. The same reasoning explains why gravity is irrelevant here. Photons carry energy and therefore gravitate, but gravitational interactions are unimaginably weak compared to electromagnetic ones at microscopic scales. A photon passing near an electron will scatter electromagnetically long before gravity has any measurable effect. Light sees electrons not because they are abundant, but because they are responsive. The idea that photons pass through nuclei unhindered often feels counterintuitive because nuclei contain most of the mass. But mass is not the currency of electromagnetic interaction. Charge is. And charge, when locked inside heavy, tightly bound systems, becomes effectively invisible to passing light. This explains a quiet but crucial distinction. Matter is not opaque because it exists. It is opaque because electrons are arranged in ways that allow them to interact collectively with light. Change that arrangement and transparency follows. Glass, for example, is transparent not because it lacks electrons, but because its electrons do not have available energy states that match visible photons. Light passes through without being absorbed. Add impurities, change the electronic structure, and the same material becomes colored or opaque. Once again, electrons write the optical script. Even refraction, the bending of light as it enters a medium, is an electron effect. The incoming electromagnetic wave induces oscillations in electrons, which re-emit radiation slightly out of phase. The resulting superposition changes the effective speed of light in the medium bending its path. No nuclei are required. No solidity is involved. Only electrons responding to fields. From the emotional trajectory we have been building, this is a revealing convergence. The same electrons that refuse to overlap and create solidity are the ones that give light something to interact with. The same quantum rules that prevent collapse also enable visibility. Texture and transparency arise from the same source. And this brings us back to a deeper reframing. Light does not illuminate matter. It negotiates with electrons. Every image you have ever seen, every spectrum ever measured, every astronomical observation ever recorded, passed through an electron before it reached a detector. Telescopes do not see stars directly. They see electrons in sensors, responding to incoming photons. Even observation itself is mediated by electrons. This makes electrons not just constituents of matter, but gatekeepers of information. Photons carry messages across the universe, but electrons decide which messages are received, altered, reflected, or erased. In that sense, the universe is readable because electrons exist in precisely the way they do. The unsettling implication is that most of reality is optically silent. Nuclei, dark matter, neutrinos, these pass through light without conversation. What we call the visible universe is the subset of reality that electrons allow photons to interact with. This is not a limitation of human senses. It is a structural feature of physics, and it sets up the next question. If electrons control light so completely, if they determine visibility, opacity, and the flow of information, then how do they avoid falling into the very nuclei they orbit? Classical physics predicts immediate collapse. Yet electrons persist, atoms remain stable, and light continues to interact through discrete transitions rather than catastrophic infall. The story now turns inward again, not toward size or structure, but toward stability itself, toward the quantum rules that prevent attraction from ending the universe before it can be seen at all. If attraction were the whole story, the universe would have ended before it began. An electron carries negative charge. An atomic nucleus carries positive charge. Classical physics allows only one conclusion. The electron should spiral inward, radiate energy continuously, and crash into the nucleus in an instant, on the order of a tiny fraction of a second. No atoms, no chemistry, no light with discrete colors, just collapse. And yet here we are, surrounded by matter that has remained stable for billions of years. The question is not why atoms sometimes survive. The question is why they survive at all. The failure lies not in mathematics but in assumption. Classical physics assumes that particles have trajectories, well-defined positions, and velocities at every moment. Once that assumption is made, collapse is inevitable. An accelerating charge must radiate. Radiation drains energy. Loss of energy tightens the orbit. The spiral continues until nothing remains. The logic is flawless, and it is wrong because the premise does not apply. Electrons do not move through atoms the way planets move around stars. This realization did not arrive gently. It emerged in the early 20th century as a crisis. Experiments showed that atoms emit light at sharply defined wavelengths, precise colors, not a continuous rainbow. Heated gases glowed in narrow lines, each element with its own unmistakable signature. Classical physics predicted the opposite, a smooth smear of radiation, as electrons lost energy continuously while collapsing inward. Nature refused to cooperate. The first hint of resolution came when Niels Bohr proposed something radical for its time. He suggested that electrons could occupy only certain allowed states, and that while in those states, they did not radiate at all. Light was emitted only when electrons jumped between states, releasing energy in discrete packets. The model worked mathematically. It explained atomic spectra with astonishing accuracy. But it explained nothing else. Why those states existed, why radiation turned off, why collapse stopped, these were left unanswered. The deeper explanation arrived only when electrons were no longer treated as tiny orbiting objects, but as quantum states. In this new framework, the electron inside an atom is not a point tracing a path. It is a standing wave, a solution to an equation that balances attraction, uncertainty, and boundary conditions. The nucleus does not host an orbit. It hosts a probability distribution. This is where stability truly emerges. Quantum mechanics imposes a limit that classical reasoning cannot bypass. The electron cannot be both arbitrarily close to the nucleus and arbitrarily slow. Confining an electron to a smaller region of space increases the uncertainty in its momentum. Increased momentum, uncertainty, corresponds to higher kinetic energy. As the electron is pulled inward by electric attraction, its quantum wave function tightens, and its kinetic energy rises sharply. Eventually, further confinement costs more energy than attraction can supply. The atom stabilizes not because forces cancel, but because energy has a minimum. This balance is not intuitive, but it is precise. Solve the quantum equations for an electron in the electric field of a nucleus, and discrete energy levels appear naturally. The lowest of these is not zero. It is a finite, stable ground state. The electron does not fall into the nucleus, because there is nowhere lower to go without violating the structure of quantum mechanics itself. This reframes what orbit means. Electron orbitals are not paths. They are spatial patterns, regions where the electron is likely to be found if measured. Some are spherical, some are elongated, some have nodal planes where the probability vanishes entirely. These shapes are not decorative. They encode the constraints that prevent collapse. The electron in its ground state is not circling endlessly. It is not radiating. It is not losing energy. It exists in a stationary quantum state where attraction and uncertainty coexist without motion in the classical sense. Stability is achieved without stillness and without trajectory. This also explains why atomic light comes in precise colors. When an electron transitions between allowed energy states, it must emit or absorb a photon whose energy matches the difference exactly. No intermediate values are permitted. The result is a spectrum composed of sharp lines, each corresponding to a specific electronic transition. Hydrogen's spectrum is not a continuous glow, because hydrogen's electron does not slide continuously inward. It jumps. These jumps are not arbitrary. They are governed by the same quantum structure that enforces stability. Change the nuclear charge and the energy levels shift. Add more electrons, and their mutual exclusion reshapes the allowed states. Chemistry emerges as a controlled rearrangement of these patterns, not as mechanical bonding. The emotional continuity from the earlier parts sharpens here. The same exclusion that created solidity now operates within atoms. The same probabilistic nature that erased trajectories now defines stability. The same point-like electron that resisted internal structure now spreads into orbitals that fill space without occupying it classically. What appears from the outside as a stable object is maintained internally by constraint rather than force. This is why atomic collapse never happens, not even in extreme environments. Increased temperature and electrons are excited to higher states. Increased pressure and orbitals distort. But as long as quantum rules remain intact, a lowest energy configuration exists. Collapse is forbidden not by repulsion, but by the structure of allowed states. The nucleus itself plays a surprisingly limited role here. It provides the electric field, but it does not capture the electron. In fact, the nucleus is almost irrelevant to the detailed shape of most orbitals beyond setting the scale. The electron's behavior is governed primarily by quantum mechanics, not by nuclear mechanics. This insight reshaped physics permanently. It meant that stability could no longer be explained by balancing forces alone. It required a theory where allowed configurations were discrete, where motion was replaced by state, and where uncertainty was not a limitation of knowledge, but a structural feature of reality. Werner Heisenberg articulated this shift most clearly. The uncertainty principle is often misunderstood as a statement about measurement error. It is not. It is a statement about the impossibility of defining certain pairs of properties simultaneously. An electron cannot have both a precise position and a precise momentum. The atom's stability is a direct consequence of this impossibility. Remove uncertainty and atoms collapse. Remove wave behavior and spectra vanish. Remove quantization and matter dissolves. Stability is not something added to the theory to save reality. It is what emerges when the theory is taken seriously. This also explains why atoms are not miniature solar systems. Gravity allows stable orbits because it weakens with distance in a way that permits continuous motion without radiation. Electromagnetism does not. Only by abandoning classical motion entirely does stability reappear. The atom is not a failed solar system. It is a fundamentally different kind of structure. Seen from a cosmological perspective, this has sweeping implications. The early universe cooled into atoms, not because forces weakened, but because quantum states became available. As temperatures dropped, electrons settled into bound states, emitting photons in discrete steps. The universe transitioned from plasma to matter through quantum stability, not classical equilibrium. Every star shines because electrons fall between states, not into nuclei. Every element exists because collapse is forbidden. Every molecule forms because electrons can occupy shared orbitals without annihilating structure. And once again, light plays a central role. The colors of stars, the glow of nebulae, the absorption lines in distant galaxies all trace back to electrons transitioning between stable quantum states. If electrons could fall freely, light would be continuous and featureless. Information would be lost in a wash of radiation. The universe would be bright but unreadable. Instead, it is precise. The deeper message is unsettling in a productive way. The universe is not held together by resistance alone, nor by attraction balanced by repulsion. It is held together by permission. Certain states are allowed, others are not. Reality persists because quantum mechanics limits what can happen, not because it enforces what must. This brings us to a quiet turning point. If electrons avoid collapse, not by force but by structure, if their stability arises from the shape of quantum law itself, then the question of their mass becomes unavoidable. Why does the electron weigh what it does? Why is its mass small enough to allow chemistry, yet non-zero enough to anchor atoms? The rules have kept collapse at bay. Now we must ask where those rules set their scale. The next layer of the story lies not in attraction, but in origin. After learning that electrons avoid collapse not by force, but by quantum structure, another imbalance becomes impossible to ignore. The electron is stable. It is point-like. It governs light chemistry and solidity. And yet, in the inventory of fundamental particles, it is inexplicably light, almost embarrassingly so. Compared to quarks, to the W and Z bosons, even to its heavier cousins, the muon and the tau, the electron's mass is tiny. Not just smaller by a factor of 2 or 10, but by orders of magnitude. Nothing in classical reasoning prepares you for this disparity. If mass were distributed democratically among particles, the electron should not stand out this way. And yet it does. Quietly, persistently, without explanation. The modern answer to where mass comes from begins with the Higgs field. According to the Standard Model, particles do not carry mass as an intrinsic substance. They acquire it through interaction with a field that fills all of space. The Higgs field is present everywhere, even in the deepest vacuum, and particles moving through it experience resistance that appears to us as mass. This framework is not speculative. It has been tested and confirmed with extraordinary precision. But confirmation did not bring closure. It opened a sharper question. The electron does couple to the Higgs field. If it did not, it would be massless, traveling at the speed of light, incapable of forming atoms. But its coupling strength is extraordinarily small. The Higgs field gives mass generously to some particles, and almost reluctantly to the electron. The mechanism works. The reason does not exist. To appreciate how strange this is, consider what the Higgs field actually does. It sets the scale for mass in the universe. Without it all, elementary particles would move like light, and the universe would be a thin bath of radiation and symmetry. With it, particles slow down, structures form, and time itself acquires different rhythms for different constituents. The Higgs field is not a decorative addition to physics. It is the difference between a universe that can cool and one that cannot. Within this framework, the electron's mass is determined by a single number, its Yukawa coupling to the Higgs field. That number is not predicted by the theory. It is measured and inserted by hand. The standard model contains no principle that sets its value. It simply accepts it. This is where the emotional trajectory of the story deepens. The electron has repeatedly resisted intuitive explanation. It is not solid. It is not a particle in the classical sense. It has no size. It avoids collapse through quantum constraint. Now even its mass appears arbitrary. The theory works perfectly, yet it explains nothing about why the electron is as light as it is. And this lightness matters far more than it seems. If the electron were just a little heavier, chemistry would change radically. Atomic sizes depend inversely on electron mass. A heavier electron would orbit closer to the nucleus, shrinking atoms. Chemical bonds would tighten. Reaction rates would shift. The periodic table would reorganize itself. Life, as we understand it, would likely not exist. Stars would change too. Fusion processes depend sensitively on how electrons screen nuclear charges. Electron mass influences pressure, opacity, and energy transport inside stars. A heavier electron would alter stellar lifetimes' luminosities and the balance between radiation and gravity. Even the way light escapes stellar interiors would be different. At a cosmological level, the consequences multiply. The early universe cooled through a sequence of transitions that depended on electron behavior. Recombination, the moment when electrons bound to nuclei and the universe became transparent, relied on electron mass setting the energy scale of atomic binding. Change that mass and the timing shifts. The cosmic microwave background would carry a different imprint. Large-scale structure would evolve differently. Galaxies might not form as they do. In this sense, the electron's tiny mass is not a detail. It is a condition for a readable universe. Yet physics offers no reason for it. The Higgs mechanism explains how mass arises, not why it takes particular values. This distinction is crucial. The discovery of the Higgs boson, associated with the work of Peter Higgs and others, completed the Standard Model's internal logic. But completion is not the same as understanding. The model contains more than 24 free parameters, and the electron's mass is one of the most puzzling among them. Why is its coupling so small? Why is it not zero? Why is it not comparable to that of the muon, which behaves like a heavier electron in almost every other respect? There is no symmetry that demands these values. No conservation law protects them. No deeper principle has yet revealed itself. This absence echoes the silence we encountered when searching for the electron's size. There, too, experiments returned consistency without explanation. Here again, the data are precise and the meaning is opaque. The temptation is to imagine that the electron's mass is small because it must be small for life to exist, and therefore we observe it to be so. This anthropic reasoning is not illegitimate, but it is unsatisfying. It explains observation by selection, not by mechanism. Physics has historically advanced by finding structures beneath apparent arbitrariness. The electron's mass remains a challenge to that tradition. What makes this particularly striking is how clean the electron otherwise is. It does not participate in the strong nuclear force. It does not decay. It does not reveal internal structure. It interacts electromagnetically and weakly, and that is all. One might expect such a minimal object to have a correspondingly minimal explanation. Instead, its mass sits at the intersection of quantum field theory and cosmology, unexplained and essential. The Higgs field itself does not fluctuate randomly. It has a well-defined vacuum value that permeates the universe. Particles couple to it with strengths that appear arbitrary. The electron's coupling is the smallest among charged fermions. There is no known reason for this hierarchy. The Standard Model faithfully records it without comment. From the perspective we have been building, this feels like another deliberate withholding. The electron reveals exactly what is necessary to make the universe work, and nothing more. It enforces solidity, mediates light, stabilizes atoms and anchors chemistry. while refusing to explain why it does so with such delicate balance. This delicacy is worth lingering on. The electron's mass is about 500,000 electron volts. This number sets atomic scales, molecular energies, and thermal behavior across the cosmos. Change it slightly, and familiar matter disappears. Change it drastically, and the universe becomes either too rigid or too diffuse to organize. Physics often celebrates robustness laws that hold under wide variation. The electron's mass is not robust, it is finely placed, and that fine placement is unexplained. Some speculative theories attempt to address this. Ideas involving hidden symmetries, extra dimensions, or dynamical mechanisms have been proposed to explain why fermion masses span such a wide range. None have been confirmed. The electron remains stubbornly light and stubbornly mute. This brings us back to a recurring theme. The electron is not mysterious because it behaves unpredictably. It is mysterious because it behaves perfectly while offering no deeper justification. Its mass is stable across time and space. Measurements from distant galaxies match those made on Earth. The laws governing it have not drifted over cosmic history. Whatever sets its mass did so early and decisively. From a cosmological standpoint, this constancy is extraordinary. The early universe passed through extreme energies and phase transitions. Forces separated, symmetries broke, fields condensed. Through all of this, the electron emerged with the same tiny mass it carries today. The Higgs field settled into its vacuum state, and the electron acquired its weight, never to change again. In that moment, the universe chose a scale. The choice was not arbitrary, in effect, even if it remains arbitrary in explanation. That scale allowed atoms to form at the right sizes, light to interact at the right energies, and chemistry to proceed with both stability and flexibility. The electron's mass is woven into every macroscopic phenomenon we have discussed so far, and yet when we ask why, the theory offers no answer. This is not a failure of the Higgs mechanism. It is a boundary of current understanding. The mechanism tells us where mass comes from. It does not tell us why the electron receives so little of it. That unanswered question now sits alongside others. We have encountered why the electron has no size, why its charge is exactly what it is, why it is perfectly stable. Each answer so far has removed a classical expectation and replaced it with structure without explanation. The electron does not collapse because quantum states exist. It does not reveal size because interactions say none exists. It has mass because the Higgs field grants it, but the amount is unexplained. This pattern is not accidental. It signals that the electron may be a boundary object, a place where our theories remain predictive but no longer explanatory. It behaves as required for the universe to be complex, luminous, and stable while withholding the reason for that balance. If the electron's mass is so delicately set, and if that mass underwrites everything from atomic structure to cosmic transparency, then its stability over time becomes even more significant. Why does such a finely tuned object persist unchanged, while so many other particles decay away? The next question does not concern origin, but endurance and the quiet rules that protect the electron across the age of the universe. By the time physicists accepted that the electron has no size, no internal structure, and a mass whose origin offers no explanation for its delicacy, one classical refuge still remained. Even if the electron was strange in every other respect, perhaps it still moved in a familiar way. Perhaps, between interactions, it followed a definite path through space, even if we could never see it clearly. This hope did not survive experiment. The collapse of the classical trajectory did not happen because physicists abandoned realism lightly. It happened because every careful attempt to preserve the idea of a path failed, not philosophically, but operationally. The electron itself made the idea untenable. In classical physics, motion is the backbone of explanation. An object exists at a position, carries a velocity, and traces a continuous trajectory through time. Forces bend that trajectory, but they do not erase it. To describe a system is to describe its path. This assumption worked for planets, projectiles, and even for electromagnetic waves. It seemed inconceivable that nature would violate it at the most fundamental level. Yet electrons did exactly that. The earliest warning came from diffraction experiments. When electrons were fired at crystals, they produced interference patterns identical to those formed by light. At first, this was treated as a curiosity, a sign that electrons had wave-like properties in some effective sense. But as experimental control improved, something far more disturbing emerged. The interference pattern remained, even when electrons were sent one at a time, with long pauses between them. Each electron arrived as a single localized detection. But collectively, their arrival points traced a pattern that required each electron to have access to both paths through the apparatus. If the electron had followed a definite trajectory, the pattern could not form. This is not a statement about ignorance or technical limitation. It is a statement about incompatibility. Any attempt to assign a definite path to the electron destroys the very phenomenon that reveals its quantum behavior. The more precisely one asks, "Which path did you take?" the less interference remains. The path does not merely become unknown. It ceases to exist as a meaningful concept. This forced a shift that still unsettles physics today. The electron could no longer be described as something that moves in the classical sense. Instead, it had to be described as something that contributes amplitudes to different possibilities. Motion was replaced by evolution, not of position but of probability. The mathematical framework that emerged was unambiguous. Quantum mechanics assigns a wave function to the electron. That wave function evolves deterministically according to precise equations. It does not describe a path. It describes a set of possible outcomes and their relative likelihoods. When an interaction occurs, when the electron scatters, emits light, or triggers a detector, the theory does not tell you which outcome will happen. It tells you how often each outcome will happen if the experiment is repeated. This was not a philosophical choice. It was a concession to data. Attempts to rescue classical trajectories took many forms. Some proposed that electrons had hidden paths guided by unseen variables. Others suggested that measurement simply disturbed an otherwise well-defined motion. These ideas were tested, refined, and constrained. Over time, the space for definite trajectories shrank until nothing viable remained that preserved both realism and agreement with experiment. The resistance to this conclusion was strongest in those who valued completeness in physical description. No one embodied this tension more clearly than Albert Einstein. Einstein did not dispute the accuracy of quantum predictions. He objected to what they implied about reality. A theory that could not describe what is only what is measured felt incomplete. His discomfort was not emotional. It was structural. Physics, as he understood it, should describe the world, not merely our interactions with it. The electron refused to cooperate. Experiments repeatedly showed that any attempt to ascribe a definite trajectory led to contradictions. The electron behaved as if it explored all allowed paths simultaneously, not as a physical object splitting itself, but as a mathematical summation of possibilities. Interference arose, not from motion along paths, but from the superposition of amplitudes associated with those paths. This idea reached its most refined expression in the path integral formulation of quantum mechanics. Instead of asking which path the electron takes, the theory sums over all possible paths. Each path contributes a phase. Where phases align, outcomes are enhanced. Where they cancel, outcomes vanish. The electron does not choose a path. It contributes to a pattern. Crucially, this formulation does not require the electron to travel each path in any physical sense. The paths are elements of calculation, not elements of reality. What exists are interactions and their probabilities. The trajectory is not hidden. It is undefined. This marks a profound boundary. Up to this point, every strange property of the electron could still be imagined as belonging to an object, however abstract. Probability clouds could still be thought of as something spatial. Point-like behavior could still be visualized. Even mass from the Higgs field could be pictured as resistance to motion. But the loss of trajectory removes the last classical anchor. The electron does not have a history in the classical sense. Between interactions, it does not occupy a sequence of positions. It occupies a quantum state that encodes what could happen next. Asking where it was becomes as meaningless as asking what color a sound has. The question does not fail because we lack information. It fails because the theory assigns no answer. This does not mean electrons behave randomly. The evolution of the wave function is exact and lawful. What is relinquished is the idea that reality must consist of objects moving along continuous paths. Quantum mechanics retains determinism at the level of amplitudes and abandons it at the level of events. The emotional continuity from earlier parts reaches a critical point here. Solidity vanished into exclusion. Objects dissolved into probability. Size disappeared into point-like silence. Mass appeared without explanation. Now motion itself evaporates. The electron is no longer something that goes somewhere. It is something that happens. This reframing alters the role of measurement entirely. Measurement is not a passive act of revealing a pre-existing trajectory. It is an interaction that forces the quantum state to produce a definite outcome. The electron does not reveal where it has been. It produces where it is now. This is why quantum mechanics shifts the goal of physics. The theory does not aim to describe reality as it exists independently of interaction. It aims to predict the statistics of outcomes when interactions occur. This shift is not philosophical retreat. It is pragmatic precision. Light plays a central role in this transformation. When electrons interact with photons, each exchange localizes the electron and disrupts interference. Light does not illuminate an underlying path. It destroys the conditions under which the notion of a path could exist. In trying to observe the electron's motion, we replace motion with events. This is not a technological limitation. No improvement in detectors changes the outcome. Better measurements make the disappearance of trajectories sharper, not softer. Precision accelerates the collapse of classical description. From a cosmological perspective, this insight extends far beyond the laboratory. In the early universe, particles did not trace classical paths. They existed as quantum states, interacting, decohering, and localizing as conditions changed. The emergence of classical motion of trajectories, objects, and histories is a late phenomenon. It arises when interactions suppress interference and probabilities become sharply peaked. The electron is the reason physics learned this lesson. It forced the abandonment of trajectories, not through abstract argument, but through stubborn, experimental fact. It demonstrated that prediction could be complete, even when description felt incomplete. This does not mean reality is unknowable. It means reality is structured differently than classical intuition demands. The electron is real, but not as a moving object. It is real as a participant in interactions governed by precise probabilistic rules. This distinction matters deeply. It explains why quantum mechanics has never failed a test despite its discomforting implications. The theory predicts perfectly because it asks the right question, not what is happening, but what outcomes will occur if this interaction takes place. The cost of this success is conceptual. Physics relinquishes the idea that it must describe the world as a collection of objects following paths. Instead, it describes the world as a network of interactions, constraints, and probabilities. The electron stands at the center of this transition. It is the simplest charged particle, yet it dismantled the most deeply held assumptions about motion. It did not do so dramatically. It did so quietly through patterns that refused to be interpreted classically. And so we arrive at a new kind of realism. The electron is real, but its reality is not that of a bead on a wire. It is the reality of a rule-abiding participant in quantum processes, one whose behavior is fully captured by what can be measured and not by what can be imagined in between. This prepares the ground for the next question. If electrons have no trajectories, no size, and a mass delicately set by a field, why do they persist unchanged across the age of the universe, while so many other particles decay? Stability once again emerges, not from classical expectation, but from quantum law, and the electron enforces it without exception. After the electron erased the idea of a definite path, one last expectation from classical thinking still lingered quietly in the background, that nothing fundamental lasts forever. In nature, as we know it, instability is the rule. Excited atoms decay. Radioactive nuclei fall apart. Even elementary particles, once isolated, often reveal lifetimes measured in microseconds or less. Change is built into the fabric of physics. And yet, against this backdrop of impermanence, the electron stands almost alone. Muons decay. Taus decay. Many particles transform, fragment, or disappear into lighter remnants. Quarks never appear freely at all, confined permanently inside composite states. But the electron persists, not just for seconds or years, but for as long as the universe has existed. Every electron present today could, in principle, be the same electron that emerged from the earliest moments after the Big Bang. This is not poetic exaggeration. It is a statement supported by every experiment ever performed. The natural question is not why electrons last a long time. It is why they do not decay at all. In particle physics, decay is never arbitrary. It follows strict accounting rules known as conservation laws. Energy must be conserved. Momentum must be conserved. Electric charge must be conserved. And crucially for electrons, certain quantum numbers must also remain intact. These rules do not merely constrain what happens, they define what is allowed to happen. The electron carries electric charge, and that charge is the smallest unit observed in isolation. There is no lighter particle with the same charge that the electron could decay into. This single fact already places a severe restriction on its fate. Any decay process must preserve charge exactly. If the electron were to decay, its products would need to carry the same negative charge. No such lighter state exists. This is not an assumption. It is an empirical boundary. Physicists have searched for signs of electron decay for decades. They have looked for electrons transforming into neutrinos, photons, or other hypothetical particles. None of these processes conserve charge in a way that nature permits. The absence of decay is not a mystery left unchecked. It is a conclusion reinforced by the silence of detectors. There is another layer to this stability, quieter, but just as decisive. The electron belongs to a family of particles known as leptons. In every observed interaction, lepton number is conserved. An electron carries one unit of this number. Any decay would need to account for it. Once again, there is nowhere for it to go. The bookkeeping does not allow the transaction. What makes this especially striking is that heavier versions of the electron do exist. Muons and taus behave like electrons in almost every respect. Same charge, same spin, same interactions, yet they decay readily. Their instability is not due to any flaw or weakness. It is due to opportunity. They are heavier. They can decay into lighter particles while preserving all conservation laws. The electron cannot. Here stability emerges, not from strength, but from minimality. The electron sits at the bottom of a ladder. There is no lower rung with the same essential properties. In physics, being the lightest carrier of a conserved quantity is a powerful position. It grants permanence. Protons share this privilege with respect to baryon number, which is why ordinary matter does not dissolve spontaneously, but even the proton's stability is less secure. Theories beyond the standard model allow for its decay at unimaginably long timescales. For the electron, no such pathway even exists within known frameworks. This endurance reshapes the universe on every scale. At the microscopic level, electron stability allows atoms to persist. Electrons do not vanish from orbitals. They do not quietly transform and leave nuclei bare. Chemical bonds endure because the particles that form them do not decay away. Matter remains matter because its fundamental charge carriers remain intact. At the macroscopic level, this stability governs how light interacts with matter over time. Photons scatter from electrons, are absorbed by electrons, and are emitted by electrons. If electrons decayed even slowly, opacity would change. Spectral lines would drift. The optical properties of matter would not remain fixed. The universe would not be reliable enough to read. At the cosmic level, the consequences deepen further. After the early universe cooled enough for electrons to bind to nuclei, atoms formed and radiation decoupled from matter. This transition allowed light to travel freely across space, carrying information from the past to the present. If electrons were unstable on cosmological timescales, this transparency would not last. The universe would gradually return to opacity as charge carriers disappeared. The sky would darken in ways we do not observe. Instead, the universe cools, structures persist, and information remains accessible. The electron's stability underwrites all of it. What is unsettling is how little drama accompanies this fact. There is no protective force shielding the electron from decay, no barrier it hides behind. It simply has no allowed exit. The rules of quantum mechanics and conservation law leave it with nowhere to go. Stability, once again, is not something imposed. It is something permitted. This theme has been building quietly across every part of the story. Solidity arose from exclusion, not contact. Stability arose from quantum structure, not force. Mass arose from a field, not substance. Trajectories vanished into probabilities. Now permanence arises from constraint, not endurance. The electron survives not because it resists decay, but because decay is forbidden. This reframes time itself. We often imagine the universe aging through decay, with complexity slowly dissolving. But some elements of reality are not eroded by time. They are protected by symmetry and accounting rules so strict that time has nothing to act upon. The electron belongs to this category. It does not age. It does not wear out. It does not remember how long it has existed. From a cosmological perspective, this is profound. The early universe was a violent place filled with high energies, rapid interactions, and constant transformations. Many particles that existed then no longer exist now. They decayed, annihilated, or froze out as conditions changed. The electron survived every transition unchanged. It passed through symmetry breaking, through recombination, through galaxy formation, through stellar evolution, and into the present day without alteration. This continuity allows the universe to build upon itself. Structures formed early remain legible later. Light emitted by ancient stars interacts with the same kind of electron that exists today. Physical law does not drift. The past remains interpretable because the fundamental participants remain the same. It is tempting to treat this as a fortunate coincidence, but physics does not deal in coincidence. The electron's stability is a consequence of deep principles that shape all interactions. Conservation laws are not optional. They are the grammar of reality. The electron happens to occupy a grammatical position that cannot be transformed into anything else. This also clarifies why electron stability is so tightly connected to cosmology. Without stable electrons, the universe would struggle to retain memory. Information would leak away as particles transformed. Chemical complexity would erode. Light would lose reliable interaction partners. Cooling would stall. Structure would unravel. Instead, the universe ages in a layered way. Stars are born and die. Galaxies collide and reshape. Yet beneath all this change, electrons persist unchanged, acting as anchors for physical processes across time. There is a subtle emotional shift here. Earlier, the electron felt elusive, spread out, pathless, unexplained. Now it feels immovable, not because it is heavy or rigid, but because it is placed at a logical endpoint. It cannot decay without violating the rules that make the universe coherent in the first place. And this brings us to a final tension. The electron is perfectly stable, yet it participates endlessly in interactions. It scatters light, binds atoms, conducts electricity, and responds to fields without ever transforming itself. It is dynamic without being transient. This combination is rare. It raises the final question not about what the electron does, but about what it enables. If electrons are stable enough to persist across cosmic time and responsive enough to interact with light and matter, then they become the medium through which the universe communicates with itself. They are not just constituents. They are conduits. The next step is to follow that role outward, to see how nearly every piece of astronomical information reaches us only after passing through electrons first, long before light ever touches a telescope. After establishing that electrons persist unchanged across the age of the universe, another realization follows almost inevitably. Stability alone does not explain their importance. What truly elevates the electron is not merely that it survives, but that nearly every piece of astronomical information we possess has passed through electrons long before it ever reached us. Light may be the messenger, but electrons are the authors. They decide what is written, what is altered, and what is erased. When astronomers point a telescope toward the sky, they often speak as if they are collecting light directly from distant objects. In practice, this is never the case. Light rarely travels untouched. From the moment it is produced in a star's interior to the instant it is recorded by a detector, it encounters electrons again and again. Each encounter leaves an imprint. Those imprints are what astronomers learn to read. The journey begins inside stars, where matter exists not as neutral atoms, but as a hot, ionized plasma. In this environment, electrons are not bound to nuclei. They move freely, responding to electric and magnetic fields. Photons generated by nuclear fusion do not escape directly. They scatter countless times from electrons, changing direction, energy, and polarization with each interaction. The light that finally emerges from a star's surface carries the cumulative record of these encounters. Its spectrum, intensity, and angular distribution are shaped by electron behavior long before the star becomes visible. This is why stellar spectra are not smooth. They are punctuated by absorption and emission lines, precise features created when electrons transition between quantized energy states. Each line corresponds to a specific interaction between light and electrons, bound within atoms or ions. By measuring these lines, astronomers determine the chemical composition of stars, the temperatures of their atmospheres, and the pressures under which electrons operate. The nucleus plays almost no role in this diagnostic process. It is the electron that speaks. As light leaves a star and enters interstellar space, its conversation with electrons continues. The space between stars is not empty. It contains plasma, thin, diffuse, but pervasive. Free electrons in this medium scatter radio waves, rotate the polarization of light, and absorb or emit radiation at characteristic frequencies. Signals arriving from distant pulsars are delayed and dispersed in ways that reveal the density of intervening electrons. Astronomers map the structure of the galaxy not by seeing the electrons directly, but by reading how they have reshaped passing light. In regions where magnetic fields thread through plasma, electrons spiral along field lines at relativistic speeds. This motion produces synchrotron radiation. a distinctive form of light whose spectrum and polarization encode the strength and geometry of magnetic fields. Entire classes of astronomical objects, supernova remnants, jets from active galaxies, and the diffuse glow of galaxy clusters are studied primarily through this electron-generated radiation. The light we observe is not merely reflected or transmitted. It is manufactured by electrons in motion. Even polarization, a subtle property of light, often invisible to the eye, becomes a powerful diagnostic tool because of electrons. When light scatters from electrons, its electric field becomes preferentially oriented. By measuring polarization patterns, astronomers infer the geometry of scattering environments, the presence of magnetic fields, and the alignment of dust grains. Once again, electrons mediate the interaction. Without them, light would arrive featureless, stripped of context. Cosmic opacity is another electron-written chapter. The universe is transparent at some wavelengths and opaque at others, not because of matter in general, but because of how electrons are arranged. Neutral hydrogen absorbs specific ultraviolet wavelengths because its electron transitions resonate there. Free electrons scatter microwave radiation efficiently in the early universe, rendering it opaque until recombination. The visibility of the cosmos across different epochs is a story of electrons entering and leaving bound states. This is why the cosmic microwave background exists in its observed form. In the early universe, electrons scattered photons, incessantly preventing light from traveling freely. Only when electrons bound to nuclei did scattering cease, allowing radiation to stream across space. The faint glow we observe today is not simply ancient light. It is light whose last meaningful interaction was with an electron nearly 14 billion years ago. The electron marked the moment the universe became observable. Detection itself reinforces this dependence. Modern telescopes do not sense photons directly. They rely on electrons in detectors. Incoming light liberates electrons from materials through the photoelectric effect, or excites them into higher energy states. Those electrons are then counted, amplified, and converted into data. Every astronomical image is at its core a map of electron responses to light. From this perspective, astronomy is not the study of light alone. It is the study of light's dialogue with electrons across vast scales of space and time. Spectral lines reveal velocities through Doppler shifts, because electrons respond differently when atoms move. Temperatures are inferred because electron energy distributions shape emission profiles. Magnetic fields are mapped because electrons trace them through radiation. Even gravity enters indirectly as it influences electron motion through plasma dynamics. The emotional arc we have been following sharpens here. The electron began as the hidden enforcer of solidity, then dissolved into probability, refused size, avoided collapse, acquired mass without explanation, abandoned trajectories, and persisted eternally. Now it emerges as the interpreter of the universe. Without electrons, light would still exist, but it would carry little usable information. The cosmos would glow, but it would not speak. This reframing alters how we think about observation itself. We do not observe stars. We observe how electrons in stars interacted with light. We do not observe galaxies directly. We observe how electrons in interstellar and intergalactic media modified radiation along the way. Observation is mediation, and electrons are the mediators. There is a quiet humility in this realization. The universe does not present itself directly. It allows itself to be inferred through layers of interaction. Each layer filters, reshapes, and encodes. Electrons form the most persistent and universal of these layers because they are light, stable, abundant, and responsive. From a cosmological timescale, this role is decisive. As the universe expands and cools, electrons continue to govern how information flows. They enable the formation of atoms, which enable chemistry, which enables stars, which generate light. which electrons then shape and transmit. The entire observational chain loops through the same participant repeatedly. This also clarifies why certain components of the universe remain elusive. Dark matter interacts gravitationally but not electromagnetically. It does not couple to electrons. As a result, it does not write itself into light. It shapes the cosmos silently, detectable only through indirect effects. The visible universe, by contrast, is the portion that electrons allow photons to interrogate. In this sense, visibility is not a given. It is a privilege granted by electron interactions. The universe is readable because electrons are willing to respond to light in structured, predictable ways. Change their properties, and the language collapses. Spectra blur. Polarization vanishes. Signals lose coherence. The cosmos becomes harder to decode. The continuity from earlier parts now feels complete. The same electron that prevents matter from collapsing into featureless density also prevents information from dissolving into noise. It enforces structure in both substance and signal. It is not merely a particle among others. It is the interface between matter and meaning. And yet, this interface raises a final, unresolved tension. If electrons are the medium through which the universe becomes knowable, and if they obey quantum rules that resist classical description, then our picture of reality is inherently indirect. We never see the universe as it is. We see it as electrons allow it to appear. This does not weaken science. It defines its power. Astronomy succeeds not by bypassing electrons, but by understanding them so well that their imprint can be reversed, decoded, and interpreted. To read the cosmos is to learn the grammar of electrons. And with that grammar in hand, the final question no longer concerns what electrons do for us, but what they ultimately are within the deeper structure of reality. A question that remains open, even as their role in shaping everything we see becomes undeniable. After following the electron across solidity, probability, size, light stability, mass motion, endurance, and information itself, one expectation quietly dissolves: that all of this effort should culminate in a final explanation. Not a summary, not a metaphor, but a reason why the electron is exactly what it is. That expectation remains unmet, not because physics has failed, but because the electron has done something more unsettling. It has obeyed every rule perfectly, while refusing to explain why those rules take their particular form. A century of experiments has not loosened this grip. The electron fits quantum electrodynamics with extraordinary precision. Its charge, mass, spin, and interactions are measured, predicted, and confirmed to more decimal places than almost any quantity in science. When electrons scatter light, the theory predicts the outcome. When they bind into atoms, the structure follows. When they carry current, conduct heat, emit radiation, or mediate chemistry, the calculations work. There is no crisis of accuracy here. There is a crisis of closure. The deeper one looks, the more the electron appears less like an object, and more like a rule that happens to participate in interactions. This is not how physics usually unfolds. Historically unexplained regularities eventually give way to deeper mechanisms. The motion of planets yielded to gravity. Heat yielded to molecular motion. Electricity and magnetism unified into fields. In each case, something beneath the surface explained the surface behavior. The electron has resisted this pattern. Every attempt to explain its properties by invoking smaller parts or hidden structure has failed experimentally. Every attempt to derive its mass charge or coupling strengths from first principles has stalled. The Standard Model accepts the electron as given. It tells us how it behaves, not why it exists with these particular numbers. The Higgs field grants it mass, but not meaning. Quantum mechanics governs its evolution, but not its origin. Electromagnetism dictates its interactions, but not its scale. The theory is internally consistent and externally exact and conceptually unfinished. This is not a flaw in calculation. It is a boundary. The unresolved tension becomes sharper when gravity enters the picture. Gravity governs the structure of the universe at the largest scales. Electrons govern visibility, chemistry, and matter at the smallest. Yet the two frameworks describing them, general relativity and quantum field theory, do not coexist comfortably. The electron interacts gravitationally because it has mass, but gravity remains negligible in its quantum description. Attempts to quantize gravity or embed electrons within a deeper spacetime framework have not yet succeeded. This gap matters because it hints that the electron may sit at a junction between theories rather than within one of them. It behaves exactly as quantum field theory demands, while inhabiting a universe shaped by spacetime curvature. It is affected by gravity without revealing how gravity fits into the quantum rules it follows so faithfully. The electron does not violate either framework. It exposes their separation. From a cosmological perspective, this separation is striking. The early universe required both quantum behavior and gravitational dynamics. Electrons existed during epochs, when space-time itself was evolving rapidly. They emerged with fixed properties and retained them as the universe expanded, cooled, and structured itself. Whatever set those properties did so in conditions far beyond our current experimental reach. The temptation is to treat this as a mystery in need of embellishment. But the electron does not invite drama. It invites discipline. As Richard Feynman once observed, nature does not explain itself. It shows its rules. The electron is one of those rules. It does not announce its purpose. It does not justify its parameters. It simply behaves consistently and exactly across every domain we can test. This perspective changes what explanation means. Perhaps the final explanation is not a story beneath the electron, but the recognition that certain features of reality are foundational rather than derived. The electron may not be explained by deeper structure in the way classical intuition expects. It may be one of the structures from which explanation proceeds. Seen this way, the journey we have taken resolves into a different kind of understanding. The electron began as the hidden cause of solidity, enforcing exclusion where contact seemed obvious. It then erased the notion of particles as objects, replacing them with probability. It refused size, revealing point-like silence under intense scrutiny. It shaped light, prevented collapse, gained mass without explanation, abandoned trajectories, endured across time, and became the medium through which the universe speaks to us. At each step, explanation gave way to constraint. The electron does not tell us why the universe is readable. It is the reason the universe is readable. Light interacts, atoms persist, spectra form, information survives, and observation becomes possible because the electron behaves exactly as it does, and not otherwise. This realization carries a quiet humility. Physics is often portrayed as a ladder of deeper answers. The electron suggests a different image, a set of pillars. Some questions do not lead downward. They lead inward toward acceptance of structure without narrative. The success of science here is not in dissolving the electron into something simpler, but in learning to work precisely with what cannot yet be reduced. This does not mean inquiry stops. It means inquiry changes its aim. The unanswered questions surrounding the electron, its mass scale, its coupling hierarchy, its relationship to gravity, are not loose ends. They are signposts marking where current frameworks meet their limits. Future theories may one day connect these pieces, or they may reveal that some elements of reality are primitive in the deepest sense. Either outcome preserves what we already know. The electron's behavior will not change. Its role in shaping matter and light will remain. The universe will continue to be legible through it, even if its ultimate explanation remains out of reach. There is a certain calm in ending here, not because all questions are resolved, but because the picture is stable. The electron does not flicker between interpretations. It does not surprise us with inconsistency. It stands as one of the most reliable features of the physical world, even as it resists philosophical closure. And that resistance is not failure. It is a reminder of scale. Human understanding advances by mapping rules, testing them, and learning where they apply. The electron has been mapped with extraordinary care. It has passed every test. It has earned its place as foundational. Thank you for spending this long journey here, following an idea so small that it shapes everything, yet so exact that it needs no explanation to keep working. Your time, your attention, and your curiosity are never taken lightly. Wherever you are listening from, and whatever weight the day may have carried with it, I hope these thoughts now feel settled, complete enough to be left behind until tomorrow. May the same calm rules that keep atoms stable and light readable carry you gently into rest. Good night, and sleep well.